ChatGPT may seem as if it has been part of our lives for centuries, yet you might not even have heard of GPT-1, which was introduced in 2018. The famous ChatGPT you know was born in November 2022, less than 3 years old. Today, GPT-4, accessible for about $20 a month, entered our lives on March 14, 2023. These milestones feel so recent that they are almost as if they were invented yesterday. The impact of ChatGPT has been immense. It has not only popularized large language models, but also spurred the development of other systems such as Claude and Llama, other language models, Sora for video generation, and Suno for music generation. This wave of innovation has changed many aspects of technology and creativity. Have you ever wondered how all of this works? How can a piece of software not only understand what a picture contains, but also solve underlying mathematical equations, and then even explain the solution out loud? How can it simultaneously generate a poem reminiscent of Nazim Hikmet's style and deliver a lecture on quantum mechanics? What exactly goes on under the hood of these systems, and how does a machine learn in the first place? At its most basic, traditional software or algorithms are like rigid recipes. Given the same input billions of times, they produce the same output without fatigue or error. Think of a calculator, Excel, or even the URL bar in your browser. These systems are deterministic. However, while such determinism brings speed, it also limits the diversity and richness of possible outputs. Intelligence, as we understand it, depends not on strict rules but on flexibility and adaptability. This need for non-deterministic behavior led to the development of probabilistic statistical tools, and ultimately to artificial intelligence, AI. Modern AI systems are more stochastic by nature, meaning that while they can produce different answers on each run, their unpredictability is controllable. Even though they sometimes generate hallucinations, errors, their answers remain consistently accurate enough for many applications. Let's break down one of the most well-known AI models, GPT, which stands for Generative Pre-trained Transformer. Generative indicates the model's ability to produce creative, original content. It does more than merely copy and paste. Pre-trained means the model is initially trained on a massive, diverse dataset. Later, it can be fine-tuned for more specific tasks. And transformer refers to the underlying deep learning architecture that revolutionized natural language processing and many other fields. In the current AI revolution, the T, transformer, is arguably the most significant component. To understand transformers, we must first look at deep learning and artificial neural networks. These networks are inspired by the neural architecture of the human brain, a concept that originated in 1958 with the perceptron. Our brain consists of billions of neurons interconnected by synapses. Under a microscope, neurons show complex structures with dendrites, branching projections that receive signals, cell bodies where biochemical changes occur, and axons, long projections that transmit electrical signals. While our neurons do not literally fire like computer circuits, they communicate via bioelectrochemical signals, forming the basis for processes like perception, thought, memory, and learning. Artificial neural networks aim to replicate these processes. In a typical network diagram, each circle represents a neuron or unit that performs a simple mathematical operation. For example, input neurons, often colored green in diagrams, represent raw data, analogous to our sensory organs. These neurons send signals along weighted connections, represented by lines with numerical multipliers, to subsequent layers. The strength of a connection, a value between 0 and 1, determines how much influence one neuron has on another. Each neuron sums the weighted inputs, adds a bias term to adjust the firing threshold, and passes the result through an activation function, such as a sigmoid, to normalize the output between 0 and 1. In simple terms, each unit in a neural network is a tiny calculator that takes in numbers, the inputs, processes them through basic arithmetic, and outputs a value. These units are organized into layers: an input layer, receiving raw data, one or more hidden layers that extract and transform features, and an output layer which provides the final result. For example, if we want to teach a neural network to recognize handwritten digits, we might use images of size 28 by 28 pixels. Each pixel's brightness, from 0 for black to 1 for white, becomes an input. With 2828 pixels, the input layer consists of 784 neurons. The output layer might have 10 neurons, each corresponding to one of the digits 0 through 9. The hidden layers learn to detect features such as curves, edges, and other patterns that define each numeral. After processing, the output neuron with the highest activation, closest to 1, is taken as the network's prediction for the digit. Training such a network is achieved by initially setting all weights randomly, so the network's early outputs are essentially random. Then, using a large and well-labeled dataset, for instance a collection of handwritten digits with correct labels, we adjust the weights using a method called backpropagation. This process penalizes incorrect outputs and rewards correct ones, similar to how one might train a baby or a pet. A cost function quantifies the difference between the predicted output and the actual label. The goal is to reduce this cost over time by fine-tuning the weights. Techniques such as gradient descent are employed to roll downhill in a multi-dimensional error landscape, eventually reaching a point where the cost is near zero. At that point, the network reliably recognizes inputs, even ones it has never seen before. Despite all these advances, many aspects of how these networks work remain mysterious. In many cases, even after training, we refer to these systems as black boxes because we cannot fully explain how the hidden layers process inputs to produce the correct output. This is analogous to our own brains. While we know the overall functions, the exact details of how billions of neurons collectively yield cognition remain largely unknown. Recent research by companies such as OpenAI and Anthropic is beginning to shed light on these mysteries, and we can expect further insights in future videos. In short, much like our understanding of the human brain, our grasp of AI's inner workings is still evolving. Yet despite the gaps in our knowledge, these systems work remarkably well. Moreover, while traditional views of AI may dismiss it as merely a statistical engine that picks the most likely next word or output, consider that human communication and decision-making follow similar statistical principles. We plan actions, choose words, and even solve problems by evaluating probabilities. In many ways, both human and machine intelligence are built upon the same fundamental idea, making the best decision based on available data. As the field has advanced, additional layers and more complex architectures have been added to basic neural networks, giving rise to deep learning. Innovations like convolutional neural networks, CNNs, have revolutionized image recognition, object detection, and facial recognition. Recurrent neural networks, RNNs, have dramatically improved language translation, sentiment analysis, and speech recognition. Generative adversarial networks, GANs, pit multiple networks against one another to produce stunning outputs in image generation, enhancement, and even text production. Today's state-of-the-art image generation systems, such as those behind Midjourney or Sora, use diffusion models, a topic that will be explored in future videos. All these advanced models still rely on the neural network architecture at their core. Although there is a huge gap between biological neural networks and those implemented in silicon, we have already managed to capture many of the brain's essential functions within machines. For example, if I show you a set of letters that look different at first glance, your brain quickly recognizes them as instances of the same letter A. Thanks to our understanding of neuroscience, we can design algorithms that mimic this pattern recognition ability. If you want a machine to read handwriting, one approach is to use pattern recognition by breaking an image into pixels, assigning each pixel a numerical value based on its brightness, and feeding these values into a neural network. With enough data and training, the network learns to associate specific pixel patterns with particular numerals. For instance, if the network's input layer has 784 neurons from a 20 by 28 image, and its output layer has 10 neurons, representing digits 0 to 9, then, through a series of hidden layers, the network learns to extract the features that define each numeral. The neuron in the output layer that is most activated becomes the network's final prediction. Training involves presenting many labeled examples, such as in CAPTCHA challenges, and adjusting the network's weights using backpropagation. This method modifies the strength of connections between neurons based on the error of the network's prediction. The process is analogous to how our brain's synapses strengthen with learning and weaken with forgetting. Over time, as the network sees more examples, its overall error, as measured by a cost function, decreases. Eventually, even when presented with a numeral it has not encountered before, the network can accurately predict the correct label. Yet, many aspects of these hidden layers remain opaque. While we can observe that a network accurately recognizes an input, we often cannot explain in simple terms how it makes that decision. This is why many advanced AI systems are called black boxes. In recent years, research from OpenAI, Anthropic, and others has begun to illuminate these processes, although many details will remain topics for future videos. If you don't want to miss those insights, be sure to subscribe and turn on notifications. In summary, while we do not fully understand every detail of why AI works as it does, the systems operate effectively, much like our own brains, which are themselves marvelous statistical machines. Both human cognition and machine learning rely on evaluating probabilities and making optimal decisions based on data. Over the years, additional layers and novel architectures, such as CNNs, RNNs, GANs, and diffusion models, have been developed to overcome the limitations of earlier methods like backpropagation, leading to the robust and versatile AI systems we see today. One of the pivotal breakthroughs came in 2017 with the development of the transformer architecture. This innovative model, which introduced the concept of attention, fundamentally changed how AI systems process sequences of data. Imagine teaching a child something new. If the child's attention wanders, the lesson is lost. Similarly, for AI, the attention mechanism helps the network focus on the most relevant parts of the input. In practice, transformers and their attention layers allow models like ChatGPT to weigh recent inputs more heavily, improving the coherence of generated text. This idea, combined with techniques such as embedding, mapping words or tokens into a continuous vector space, enables the AI to grasp contextual meanings. In this vector space, similar words or tokens lie close together, allowing the network to capture semantic relationships and generate meaningful responses. While the underlying mathematics of these processes might seem daunting, often involving multidimensional cost functions and gradient descent across billions of parameters, the basic intuition is straightforward. At its heart, AI is about finding patterns in data and optimizing the system to reduce error. As a result, given enough high-quality data, even a machine initially producing random outputs will, through iterative training, learn to perform tasks such as language translation, image recognition, and creative generation with impressive accuracy. Many critics claim that AI is just a statistical engine that picks the most likely next word or output. However, consider that human thought, communication, and decision-making are also based on statistical evaluations of probabilities. In both cases, the process of selecting the most appropriate outcome is central. As the field continues to evolve, researchers are exploring even more advanced approaches, such as allowing software architectures to evolve on their own. Imagine a future where non-carbon-based machines develop their own optimal architectures, potentially leading to entirely new forms of intelligence. In conclusion, the revolutionary developments behind GPT, deep learning, and modern AI have transformed how we interact with technology. From the early days of rigid, deterministic software to today's sophisticated, multi-layered neural networks, our journey has been driven by the need to capture the flexibility and creativity inherent in human intelligence. While there is still much we do not understand, both about our own brains and about the AI systems we build, the progress made so far is nothing short of remarkable. As research continues and new architectures emerge, the potential for AI to evolve and adapt may one day lead to machines that learn and innovate in ways we have yet to imagine. Thank you for watching. If you found this explanation intriguing, be sure to subscribe and turn on notifications for future videos where we delve even deeper into the mysteries of AI and the brain. Until then, see you in the next video. Goodbye.